This is, I hope, interesting story of one of the research projects that I'm currently working on. As you're going to see very soon, there's three aspects of research that we're trying to do this on this project. The particular one that I'm going to talk about is how we trying to integrate a building information modeling with a sustainable design. It is, or shall I say, the case study that we're working on of the building is a retirement home for locally renowned, actually nationally renowned architect, whose name is Derek Latham, and his concept of the building is energy plus, carbon negative, and autonomous house. I'm not going to go into detail as to how we and which level of autonomy we will achieve, but if you find it interesting, please feel free to ask the questions. The context for this today presentation is really looking to almost go beyond the level 2 to level 3 by trying to understand from research point of view as to how we could integrate a building information modeling with a real-time building performance real-time. So how do we create a link between the two? There are obviously many bespoke systems on the market, but very few of them are integrated with mainstream BIM technologies. The research method is based on the case study. I think Simon's quote here explains it all. Often we ask from our students to prove or disprove their research methodology. I think the case study here in terms of the in-depth exploration from the multiple perspectives, complexity of the real-life context, with the primary purpose of generating in-depth understanding of something is all kind of advocates for use of the case study as one of the research methods that we should always consider. The building, which I will talk about first, or how shall I say, before we actually move on to the main parts, is situated in the Little Eaton, which is, as you can see, quintessential type of the countryside setting on the edge of the Peak District, which is second most visited park in the world, from what I know. And please note that all of these woods here, so this is existing house, and we are going to be building here. We are building here. Sorry, we've been building for now over 23 months. But all these woods here actually belong to the original house. The original house is 1920s arts and crafts type of the house, quite cute itself. I think it tends to sell here and basically live here. So the reason I'm pointing out these woods because they will become important in a couple more slides. The building will actually be situated, as I said, on this location here, where there was formerly a greenhouse foundation, or used to be a greenhouse there, and very much in terms of both roof line and sight lines, as well as in terms of the concept, trying to be contextually sensitive and working with defining local characteristics in paragraph 55 project, basically. It was a very, very important to obviously design something that was non-intrusive to such a beautiful beautiful context. So you will see a kind of quick mock-up visual in a couple of slides, but just to understand what the house proposal is quickly, it's an upside-down house, so accommodation, sleeping accommodation is on the ground floor, with each of the bedrooms having their own suites and the circulation area being there, going to the first floor of the staircases. This is a plant room and the de facto the garden store. Moving on to the upper ground level, we call them lower ground and upper ground levels actually, rather than ground first floor. Leading onto quite open, well, very open, shall I say, plan organization with a staircase leading onto the next level, which is a mezzanine level office, and this is a kind of de facto sitting, dining, and kitchen area put all together. And then, as you can see here on northern side, it's actually walkable roof. So this part of the roof is walkable. There are no windows on northern side. This is a 7.8 meters concrete retaining wall connected to the factor rough foundation, as you're going to see in a couple of images, and you can see there also in the section. That's a more kind of artistic impression of what we are aiming for. Some of these things have changed. This was originally supposed to be a roof that is made of aesthetically equal panels combined between skylights, solar, hot water and PVs. At the moment we don't no longer need solar hot water, i.e. we will be able to get all the electricity need pure through the electricity generation, all the heating needs pure through electricity generation. So this will be a combination of the PV and the skylight panels of equal aesthetic value. And notice how quite nicely is blended into the landscape. There are three key areas of the research that we're looking here. I know order of importance. First one is I use the sycamore as a structural material because currently building regulations do not allow sycamore to be used as structural material due to its perishability. We feel it can. We have worked out its mechanical properties that are actually a par of the oak. It is a hardwood. The problem is it is very perishable timber if its moisture content is increased or kept in prolonged periods over 20%. So detailing out any prolonged contact to high humid environments and monitoring regularly what is the moisture content of the sycamore is the way that we're going to approach this project. I wish I had photographs out because we just laid out all of this structural timber frame, but I put this presentation before I took the photograph. I can send it to anybody who would like to see. So obviously that's a research in its own right, because obviously we want to see how the sycamore will perform. The reason we use the sycamore is, by the way, connected to the first image I've shown you. All those woods are woods of the sycamore, which we thought it would be great to use in terms of the local sourcing of the materials, and also allowing some arguably more noble species to get a go, since the sycamore is actually quite an invasive type of the species. Also, we're using a dry stone walling, which again is very useful for us because the whole house sits on the ex-used quarry. So basically, when we're talking about local sourcing material, it doesn't get much more local than this. And we're using hemp walls, which we originally wanted to grow next door in agreement with the farmer. For practical reasons, we had to move to a commercial company in terms of supplying the hempcrete, but the transport is about 18 miles, so it's a fairly local. Early image on the side, cut into the side of the garden, ground floor slab or rough foundation prepared for ground floor slab casting, walls going on the side. This is this 7.8 meters retaining wall. It looks quite imposing, but as you've seen from the image mock-up, the whole thing will be coming quite in the context, because half of this is missing, and you won't be able to see any concrete because there will be basically a dry stone walling in front of every single piece of concrete. So actually, we'll not know about the concrete. Yes, we use lots of concrete. So one of the questions that we often get, well, what about all these local sourcing of the materials if you use that much cement to that concrete? True, we've got obviously thermal mass, but also what we have done is we have specified a 80% GGBS concrete. At the time of the markets, we could not find any greener product. So I don't know whether there is a higher possible replacement, but that's the highest that we could find at the time, and that's what we have used in terms of the cement replacement. In terms of the BIM integration, this is probably the key slide for this presentation. What we try to do is integrate the concept of something that I've been doing research some years on now, and published in one of the architecture technology books, of the sustainable design analysis, where I define that as a not what we do on the part L end, but something that we should be doing more in terms of rapid and quantifiable, and I mean next day design meeting feedback within the office. So how do we train professionals? And my argument is going to see this presentation, architecture technology students are, or architecture technologists are ideally suited for this, is what kind of professionals do we need to train to give quantifiable feedback to some of the qualitative design thinking that can be employed next morning in terms of decision making. And I mean literally, what happens to the building in terms of solar gains if we are to rotate it 15 degrees on the side? I can't be going to parcel consultants every time I got a question like that to pay him £7 or £8 or £1,000 and then wait 2 weeks to get results. We need to get those kind of feedbacks within the office, because we all know that the early decisions or decisions made early in design tend to have highest cost impact, i.e. the costs of decisions are their lowest, but the actually cost impact could be the highest. And that fastly diminishes as we progress through design. So ideally, we should be making the most of the important decisions as early in design as possible. That doesn't happen at the moment because most of us do parcel compliance 2 or 3 weeks before we go to site, or a week before we need a building control approval. So however good or bad it is, it's too late to change anything. Fine. So we have undertaken full analysis, looked at the carbon neutrality of the building, looked at the solar gains and the generally solar analysis. Notice this west end window, because we have noticed obviously is vulnerable, and that's a part of the project that we're going to consider in terms of the BIM integration. Light level analysis, temperature profiles in buildings. We also done, rather than just trusting software, we also done a calculations from the first principles. So basically working with Valiant, we did calculations of key aspects of performance. You notice here we had 10 scenarios depending on what flow temperature of air to water heat source pump we do, dropping it down from 40 to 35 degrees. We have managed to get ourselves in the both carbon neutral region, i.e. numbers are negative here, and also because we are generating 6,093 kilowatts of the PV generation, we also managed to get in energy plus position, i.e. creating more energy than we need and exporting it to the exporting back to the electricity network. We've also went with the students and built a small-scale building. These are some of my master students, some of them here. Actually, one of them is now working for Kingspan, and she was working there, Claire. We've designed it, we built it together with the students for 2 or 3 days, using hempcrete, exactly same construction. Half of the construction is a sycamore frame, half of construction is a normal, traditional softwood timber frame, and we are now currently doing measurements and comparing the two. So you can see some of the images of the work. There is a shuttering taken off. This is a test building de facto. Lime rendered on the outside. Measurements, relative humidity, temperature, moisture content. We literally track it on the mobile. Each of these sensors are $7. So very few excuses now for us not to monitor buildings anymore. We can get these technologies in terms of monitoring for almost, I don't know, for example, in the range of $100 to $120, we could monitor wirelessly whole of the building in terms of the key monitoring parameters, temperature, relative humidity, and moisture contents. And we should be doing because the performance gap is still too big. In this particular measurements, we concluded that actually sycamore moisture content was 21%, which is 1% above what we wanted to keep it. A slight concern. We realized that here, as you can see, as you can see here, we got OSB board on both sides. We struck this OSB board off on the other side, but this is fairly unbreathable OSB board, which we kept on inside, and they painted it. This is in Hill Holt Wood in Lucan. They painted it with an equally non-breathable paint, so therefore the wall was not able any longer to breathe properly, and that's one of the reasons why a moisture, the content is slightly higher than we expected. So on the final build, which is in terms of detailing, which is a lesson that we learned from this experimental build, we are going for fully breathable solution. So notice here you've got dry stone walling, are hempcrete 450 millimeters, and then here, sitting in situ of the hempcrete is the sycamore frame. There is no vapor checks, no breathable membranes, nothing, just fully breathable wall. Monitoring strategy for the boats or the buildings, and this is the part in terms of the integration. We have managed to work out proof of the concept as to how you can model a virtual sensor within the BIM environment and connect it to the real sensor on the side and get information exchange real time through a BIM platform. We managed to work that one as a proof of the concept, and we're now working as to how we can apply further in the research. So, in the conclusions, what is that we found on this project is that knowledge and understanding of sustainable design and BIM integration is still beyond small to medium practices and is not likely to be achieved in the near future, but something that I feel we should be looking certainly more in, because to close the performance gaps, we should be able to integrate our sustainable designs with our performance real time and close the feedback loop. Otherwise, we will always have a discrepancy of what we think happens on the desktop and what actually happens in real world. So we must close that loop, and I feel the BIM should be an ideal platform to retain the information in the loop rather than bespoke BMS systems. Sustainable design analysis does help produce better designs. We have managed to save 30% energy in our iterations alone, but the BIM integration at the moment with the other systems is neither faultless nor is fully interoperable. This particular project, we do understand that it is very hard to scale up because not everybody is lucky to be able to source that timber and the stone from the sites, but we feel there's still as a one-off project, an interesting project to look at and some lessons to be learned. And in summary at the end, it is very important to understand, as somebody referred to it earlier on, that of course it is not just about the software integration. More importantly, it is about investment in the shift in the knowledge and design management, because for this particular system to work, we have to have architecturally educated professionals with the knowledge of some sustainable design software in the office, so that we can get a rapid feedback straight away, almost on daily basis, where the key decisions has to be made. For people that are interesting for this project, what we're going to be monitoring very soon, we'll obviously install some of this equipment. We will be monitoring sycamore performance, very essential for us, because obviously whole building literally stands on the quality of what we do. On this, it is a timber frame building. We've got earth tube that is not part of this presentation, but obviously there we need to measure humidity, temperature, CO2, VOCs, airspeed and the pressure, and do some additional CFD simulations. And also we need to monitor hempcrete, because the sycamore is sitting hempcrete, so we need to understand the correlation between relative humidity of the hempcrete itself and the moisture content of the sycamore. We've also used some specialist health and well-being monitoring, because we believe that breathable walls are healthier than not breathable options. We will see whether we can prove that or not. Thank you.